Hey, 12th graders, we are wrapping up 14.1 with finishing talking about finding integrals. So with our last notes, we were finding integrals in the general form, and the general form pretty much means that we were adding that plus c. And the reason why we call it the general form is because it is a representation of all of the possible original functions that would lead to have a derivative of this, right? So, sorry, my coffee maker's going. So we have some sort of constant that would go away if we derived this polynomial, and it would go away. And so this is kind of a representation of all of the possible original functions or all of the possible integrals of that function. And so when we are looking for a specific one, when we're looking for one that is only the original function that represents the situation, we find the specific or the um, indefinite integral. So I want to remind you really quickly about some relationships here that you're going to see in this example 3, and you're just going to see a lot in a lot of the problems that we go through with calculus, and especially now that we know integrals, is the relationship of position to speed and then acceleration. So this is a relationship that's very important if you're going to take physics at all. This is going to be something that you talk about a lot. They sometimes call speed displacement. A lot of times in physics, they call it displacement, to be displaced a certain amount. Speed, a lot of times they call velocity. Not quite the same thing. Velocity can be negative, right? Because velocity is also telling you a direction and not just how fast. So it's fine if your velocity function has negative values, for instance. So this is a relationship that now we know that if we had y as our original function, then our speed or our velocity would be the derivative of that. And we've talked a little bit about the fact that acceleration would be the change of your speed, right? Speed is the change of your position. Acceleration is the change of your speed. So your acceleration is your second derivative of the original function. So how we move from one of these to the next is by moving down this list, we find the derivative. So moving down this list, going from here to here to here, it's all finding derivatives. And so now that we know that integrals are just the anti-derivation of a function going backwards on a derivative, we know that then also moving up on this list would be your integrals. So keeping that relationship in mind is a good thing. A skydiver's vertical velocity is modeled by the function v of t equals negative 9.8t, where v of t is her vertical speed in meters per second, and t is the time in seconds since she jumped out of the airplane. Hey, we're only looking at the first 10 seconds. The airplane has an altitude of 3,900 at the instant the skydiver jumps out. So for a second here, it says find a specific function for s of t, the altitude of the skydiver. Specific function is a specific integral. So in other words, it means no more plus c. We now need to figure out what c is as a value and make sure to have that be a part of the equation. And then the altitude here is the position, right? The altitude is their height, their vertical displacement. So we're looking for position. There we go. So if we have v of t, which is our velocity, and we want to go to displacement, that means that we need to find the integral of this function right here. So we want to find the integral of v of t. So we have that coefficient, negative 9.8, and then we raise t to the second power now. We go up by 1 power, and then we have to divide by that 2. And then we still have that plus c at the end for now. We can simplify that out just a little bit. by dividing negative 9.8 by 2, in other words, multiplying it by half, and that would be negative 4.9 t squared plus c. And that's your general form of the equation, right? Not your specific form of the equation. So now we need to move on from here. This is the first step of to just find the general form. And your second step then would say, okay, well, I don't want a plus c. I have this plus c, well, and I don't really want it there. And so if I have an unknown, I need to have one equation. If one unknown means one equation. In other words, we need to have one more piece of information here in order to solve for c. And so our thoughts here when we come across this in problem solving of like, okay, I have this thing, I don't want it to be here, I need to find a way to get rid of it, is you're going back and you're looking for other hints, other clues, other things that are going on in this problem that can help you then plug in for that. And so going back and looking at that equation, trying to find any information that we can use in order to solve for C, notice that it gives us one extra piece of information at the very, very end of the problem. It says the airplane has an altitude of 3,900 meters at the instant the skydiver jumps out. This is a relationship between time and displacement. It is a point on your original, now that we know, it's a point on your position, your displacement function, right? And so if the initial time, right, at the instant the skydiver jumps out, we say that the time is 0, right? So technically at 0, they haven't jumped yet, but the idea of the moment they jump out is like milliseconds after 0. So we just call it 0. The displacement or the height is 3,900 meters above the so when we have that information, we can plug that information in for our, this equals S of t. We can plug that in for this piece right here, right? We can plug in 0 for t. We can plug in 3,900 for the displacement. And we get that 3,900 equals c. Now that we have that, we can go ahead and write our final specific equation for this, which is negative 4.9 t squared plus 3,900. And that's the only step that we have more to learn here, is that we have learned so far how to find the plus c version, that general form. And now we're just learning that, oh, in order to find C, then we just need to have some sort of point that we know lies on whatever our new function is. What we would have before called our original function. Now it's kind of, since we're moving backwards and forwards, we need to find a different way to reference it. So we know that if we're trying to find an equation for displacement and we're missing a variable for displacement, we need to have a point that would be for the displacement. The units, sometimes when we're finding integrals, and it's easier with derivatives. Sometimes when we're finding integrals, knowing what our unit of measurement is actually very important, because you'll see in example 5, it can get a little confusing, but we just need to establish a way to find those units. And it's a very common step in these IB problems of like, hey, figure out what the unit is here. So if it says that v of t is her vertical speed, and it's in meters over seconds. So it's meters over seconds. Remember that, so how I think about this, which I don't know if this is how you're supposed to think about this, but this operation is then multiplying by your x value, right? So if this was originally, your v of t was a graph of velocity in relation to time, right? And then your equation was velocity related to time. Well, this is, meters per second, and this is per second. Then finding that area underneath is multiplying this dimension by this dimension. Let me re-explain that because I don't think I did a good job. So if you were, for the velocity function, the graph of that would have a y-axis of meters per second and an x-axis of seconds. And so in order to find the integral, remember that your integral is the area under your curve, as we talked about here in this guy, right? That your antiderivative, or in other words, your integrals, is that multiplication of those variables, of the x and the y. So in order to find then your new unit of measurement, you multiply what would have been the y unit of measurement, which here was meters per second, because velocity was your y value. And then you multiply it by your x value, seconds. And so it makes a lot of sense here that yeah, of course, our displacement would be in meters. But you'll see in example 5 where it can get just a little tricky. Okay. So it says, hence find the altitude of the skydiver at 1, 5, and 10 seconds to 4 significant figures. So now that we have this specific function and we know that our answers are going to be in meters, we can just plug these values in. We can find S of 1, right? S of 1 is negative 4.9 times 1 squared plus 3,900. Go ahead and calculate that yourself. To 4 significant figures, that would be 3,895 meters. Go ahead and find S of 5 as well as S of 10. Just plugging in 5 for t and squaring it, and then adding 3,900 after you've multiplied by negative 4.9, you get to 4 significant figures, 3,778 meters. And then plugging in 10 for t, you should get 3,410 meters. And taking a second to just be like, well, we're skydiving, right? And if we're skydiving, then our altitude is going to get less and less high. 1 second, 5 seconds, 10 seconds, right? Those jumps are happening a little bit quicker. Which makes sense if we're thinking about a quadratic and how those look and how those behave, that change is going to become much more drastic. It also makes sense in regards to what we know about skydivers, that their velocity is going to continue to increase, and so their displacement is going to grow at a faster rate as the further they go on. So taking a second being like, yeah, that number makes sense. This problem makes sense, is a really good part, a really important part of your problem solving process. Okay, so it says to find the specific antiderivative for the boundary, given boundary condition. So we have our derivative function. We want to find the original function. We want to find f of x. And we don't want to have plus c anymore. We want to be able to solve for c and have it be specific. So I'll do this one with you, and then I'll have you do the last two on your own. So in order to find this guy, we have the coefficient of 50. We bring x up by 1 exponent, so it becomes squared, and then we divide by that new exponent. Plus 25, hopefully now we can remember that when it's just a constant here, then the integral of that's just going to be adding on an x, and then we have plus c.